Hi everyone, and welcome to another episode of Mr. Carlson's Lab. I recently picked up this neat little measurement tool from way back when, and it's pretty much just the way you see it in the intro picture. So what we're going to do is see if this little device works. So we'll take a look at it, and I'll show you exactly how I hook this up. We'll hook it up together, and we'll see if we get any kind of results out of this thing. Hopefully it's somewhat alive. So let's get started. Here you are right beside me at the bench, so let's take a look at this little device. So any guesses as to what this thing is? I'll give you a closer look at this, and then I'll give you some different angles. So what we're going to do is power this thing up just the way it is. I'm not going to change any components or anything. Let's see if this thing even works. I'll explain what this is in just a moment. There you go. So make your guesses. What is this thing and what does it do? Okay, so here's the big reveal. This is a portion of an oscilloscope. So this doesn't have anything to drive the vertical or the horizontal section. So there is no vertical excitation or horizontal excitation. This is what's known as an XY display. This can be used as a modulation monitor and all sorts of different things for electronic measurement. So really what this is this is a 1-inch CRT right here, little 1-inch tube that gives us a display just like an oscilloscope. And what we're going to do is we're going to use this power supply over here to try and bring this thing to life. Let's see if this thing actually works still. So this is from, I'd say, the 50s era, like that, in that area. I think they may have even made these things into the 60s. So this looks like a really early device. You can tell by the capacitors and the way this thing is put together. So I would probably estimate in the 50s somewhere. So a nice looking little device. Hopefully the CRT is good. We'll find that out together. So what I need to do is I need to solder some wires on here so that we can bring this thing to life. What I'll do is I'll reposition the camera and I'll get closer into this thing and I'll show you exactly where I'm going to solder the wires and how I'm going to attach them to this device over here. Just before I go about attaching all the wires to this small display to try this thing out, let's take a look at the CRT. Let's remove it and take a look at it. So this is a loctile type socket, not to be confused with an octal type socket. This has a locking pin in the center. And these tubes were really good in mobile applications because they wouldn't vibrate loose out of their sockets because this little pin locks it in. So what I'm going to have to do is press on this little locking pin right here, and the CRT should just pop out. And I should be able just to pull the CRT out of this thing. So I'm going to use a plastic tool to press on this here, and I'm going to put a glove on as well, just in case I want to, say, mash my hands into the backside here. This could probably give a pretty nasty cut. So I'll just put on a glove here, like so, and grab a plastic tool that looks to be about the right diameter. And I'll just hold this like so, and I'll press right on that pin, right in the center of that pin. There it is. Take the glove off. That stands for circuit board. So I use these solely for designing circuit boards, and as you can tell, these are getting pretty soiled because they just accidentally get used for everything else. I find that I have to dedicate a pair of gloves for certain things because I find myself picking them up and using them to clean something or carry something around, and then this stuff happens. And I really don't want that on my circuit boards. So these are retired from circuit board use now, and they're now just used on the bench. This happens a lot. So get that out of the way. Get this out of the way. And that's the little CRT. 1CP1 is the number. And the getter spot is still there. It does look like it has time on it, though. And that's the base, and that's the little locking mechanism right there. So when I put this thing back in, I have to press it and it'll go click and it'll just pop in just like it popped out. So that's the little tube. Close-up view of the internals. Nice looking build. You can definitely tell by the getter spot that it does have time on it, though. All right, I'll get this thing back into this and we'll try it out. The first leads that I'm going to attach to this small display device are the filament leads. And as you can see here, it says 6.3. Now that's a dead giveaway that this is the filament. Many vacuum tubes have a 6.3 volt filament. So what I'm going to do is take these wires right here and just solder them to these pins like so. So I'll solder this one here, and I'll solder the other green one to here. Now, a very common heater color code scheme that many manufacturers use are either brown or green. So that's another giveaway. You can see that these leads are brown and they run over here to the filament pins. If one was really in doubt, you could just do a search on the pinout of the tube and that would show you that as well. But 6.3 is very self-explanatory. So I'll solder those wires on and I'll show you where those attach on the power supply over there. So what this does is this lights up a filament inside the tube. That filament heats up a cathode pipe. There's a little pipe in there, and that pipe has a coating on it. And in order for that pipe to emit electrons, that pipe has to be very hot. So the filament heats that little pipe up. So if you picture just a pipe and some filaments inside of a pipe, like you see in a normal vacuum tube, the filament itself does not touch the pipe. It's very close to the pipe, but there is no connection. And that filament glows very hot, and it causes that pipe to glow orange. And then that emits electrons. Those electrons will fly off and strike the screen, and that's what's going to give us our display on the screen. I'm going to attach the filament leads to these two terminals right here on the power supply. So you'll see that this says 6.5 volts AC, whereas the filament rating for that tube is 6.3 volts AC. The reason that they've rated this just a little bit higher is because you have to run long leads from the power supply to the device under test. And of course the device under test is our little scope, right? So there's going to be a little bit of loss in that line, especially if you're going to be drawing any type of current. The more current that you draw, the more those lines that run from this power supply start to look like resistors. So they've given just a little bit more voltage there, and of course the current rating is pretty high. It's 5 amps for this one winding here. And if I want, I can parallel these and get 6.5 volts AC at 10 amps. So the current consumption of the filament in that little tube is very small, so it's only going to use a fraction of this amount of current here. So the filament voltage is most likely going to be just a little bit high, but that's absolutely fine. Not a big deal for testing the device. So the polarity doesn't matter. I'll just plug them in any old way to these two jacks right here, and that'll supply the filament current. And what I can do is turn this on, and you'll see nothing happens here because these 2 meters are indicating what's happening with the high voltage section, and when we get to that point, I'll explain that. The 2 filament leads are now soldered onto these pins. Now what I need to do is look on this side here, and it very clearly says HV for high voltage, plus and minus. You really can't go wrong with that. So I have another 2 banana plugs here, one with a red banana plug and a black one. I think you can guess which colors are going to represent what. So the black one goes to the purple lead. I'll solder the purple lead to the negative here, and the orange lead to the positive. And that will go to the high voltage section on the power supply, and I'll show you on the power supply how that attaches as well. This is the high voltage supply right here. So this knob here, in conjunction with these 2 meters and these 2 terminals here, are what gives me the high voltage in this power supply right here. So what I have to do is turn this side on, and this has tubes in it as well, so this has to warm up. And then once it's warmed up, this thing will just turn on automatically. So you can see this is on right now and nothing's happening. But when the vacuum tubes warm up, you'll hear a big click, and this will come on over here. That should happen in just a few moments. So the negative will go to this terminal, and the positive will go to this terminal, and then I can turn the high voltage up with this right here. So anytime now, it'll go click. There it is. And you can see the high voltage here. This one goes to 500 volts. It'll give me 500 volts at 200 milliamps here. So you can see that's 500 volts right there. The filament leads and the high voltage leads are all attached to the power supply right now, and I'm ready to turn everything on. I need to be very careful because there's high voltage exposed all over this device. So the high voltage from here is lead all over this thing. So this is very dangerous, especially since I'm going to be probably putting around 400 volts on this little device right now. So unless you know what you're doing, don't try this. Let me do the dangerous stuff. If you're following along, you're doing so at your own risk. So this little plastic face on the top is insulated. So what I'm going to do is, if I'm going to adjust any of these controls, I'll just hold the plastic face and I can move these around. So I'll turn on the filaments right now. So right now the filaments in here will be warming up. There is no high voltage on this whatsoever. So hopefully this will stand up. See if that'll stand up like so. There. Stay. Okay. Is it going to cooperate? It may. Let's see what happens here. So just giving this a few seconds for the filaments to get nice and hot inside. And what I'll do now is I have my high voltage supply set to about 400 volts. That should be comfortable. It should be in there somewhere is where this thing is going to operate. So I'll turn that on right now. Hey, and there's the dot. And it's almost kind of centered and everything. That's kind of fluky. There's the center. Right about there. Wow, the thing's working. Let's try the intensity up here. Yeah, it gets pretty bright on camera. In person, it's not bright at all. So the camera's really sensitive to this right now because I've got everything nice and dark so that we can actually see this dot. But it has a dot. So I'm just going to shut the high voltage off. Make things nice and safe. So what I'm going to do now is I'm going to attach my isolation transformer and variac supply to the horizontal deflection pins, which are these two pins right here. And that should give us a trace. So if I turn my variac up, since there's AC there, what's going to happen is it's going to make this little dot sweep across the screen really, really fast and give us the impression that there's a line there. And of course, the phosphor will help that out as well. So as I turn the variac up, it should make that little line either go, longer or shorter, just depending on how much voltage I give to the horizontal deflection section here. So I'll get that all set up, and I'll show you exactly where I'm going to attach the wires on my variac as well. This is my current limited isolation transformer and variac supply. So this isolates me from the AC line, and I can also turn this outlet right here right down to 1 volt, so basically nothing. So what I can do is turn this thing on, and you'll see those bulbs at the top, those act as current limiters, and this thing is what's going to give me the horizontal deflection for that little scope. So basically I'm just going to feed AC into those two little terminals, and that should give us horizontal deflection. So what that's going to do is cause the beam on the scope to go back and forth like this, and it should draw a line on the screen. I have the horizontal deflection attached to the isolation transformer and variac supply now. So what I'll do is I'll turn the power supply on. And there's the dot. So what I'll do now is I'll turn on my isolation transformer and variac supply. And we can already see I'm getting a bit of deflection. So what I'll do is I'll advance the variac. And there it is. I'll stop about there. So what I'll do is move this over just a little bit, maybe give it a bit more intensity here. And it's looking all right. So I can move the vertical around. You can see that the tube is really strong up here, so the phosphor is really nice. And you get into the middle and it kind of dims out, and then you get to the bottom and it gets nice again. So what does that tell me? It tells me that this tube has quite a bit of mileage on it. So what's happening is this area in the center probably has burn-in on the inside of the phosphor. It doesn't look so bad on the outside, but the phosphor is tired on the inside. So you can see that bright, and then you get to the middle and it kind of dims out. And then you get down to the bottom like so, and it gets bright again. So yeah, the tube does have time on it, but as you can see, it's still usable like this. So I can turn this up even a little bit more. As you can see, if you turn the brightness up too high, it kind of fuzzes out. It gets a little bit fuzzy. This gets defocused, right? So that's about it. So here, not looking at this through the camera or anything, that's actually, you need to use this in a darker area. It looks bright on the camera, but it would definitely be hard to see in a well-lit environment. Just the shadow being cast on it from the light is even washing it out. So yeah, the tube has time on it, but it's alive, and that's a good sign. So what I'm going to do now is add more wires to this thing. So what I'm going to do is shut off the variac, shut off the high voltage, so that the thing is safe to touch. Now what I'm going to do is add another 2 wires to the vertical input here, and I'll give it a bit of vertical drive, and we'll see if we can make a neat little display on the screen. So I'll just put a sine wave in there from my signal generator. I'll get that attached, and I'll be right back. All right, let's see if we can get a signal on the screen. So what I'll do is turn on the high voltage power supply again. And there's the green dot. Now I'll turn on the isolation transformer and variac supply. And there's the line. And now I'll turn up the signal generator, which is going to feed a signal into those 2 leads right there. And there it is. It's looking not bad. Again, the center of the screen is really dim, and the camera is making this a lot brighter than it actually is in real life. But still, it's making a pattern on the screen. So down the road, in the future, on this channel, what we'll do is make a small project with this display. That should be a lot of fun. So that'll be coming up in the near future. I might even get a spare CRT for this as well. In the last video, I asked the question, why do they have an incandescent bulb on the underside of a chassis? So you can't see the incandescent bulb anywhere from the outside. It's just a light bulb shining on the underside of a chassis, and usually these bulbs are close to a regulator tube or a neon tube like this. This is an actual regulator as well. Well, the answer to that, it really is quite simple. It's just so that the bulb will ionize or strike correctly in complete darkness. If you have a neon tube and it's used in an oscillator or a sweep circuit, that tube may not ionize correctly or give erratic operation when the circuit is supposed to be sweeping. So, due to the photoelectric effect, which I have in a book, it's actually written the exact same way. Due to the photoelectric effect, what it does is it causes the tube to ionize correctly. It will make it, what would the word be? Consistent. It will strike consistently at the correct time. If you have a sweep circuit and it's not striking or ionizing correctly at the right time, the sweep is going to be erratic in the device, right? So it needs to have a light source close to it. So it needs to have some sort of photon emission very close to the bulb itself. This can very easily be seen if you have a flickering power bar in your house. So a lot of power bars have neon bulbs under the switch. So you click the switch on and the neon bulb is kind of flickery and it's not operating correctly. If you shine a light on the neon bulb, it'll stay on. And then you turn your flashlight off and it starts to flicker again. You can try that experiment yourself. So that'll give you an idea of how that photoelectric effect works. So what I'll do is I'll just move these out of the way, like so. Come down here, and I'll give you an example of a circuit. So this isn't a spectrum analyzer here. Nice discolored schematic here. So this isn't a spectrum analyzer. This is a really big schematic. This is folded and folded and folded and folded. So this thing here will stretch out and across an entire bench space. So this here is in the sweep circuit. This is a neon type bulb. And as you can see, it says DS101. This is the incandescent bulb that's close to this little neon bulb. You can see it says NE16 is the type of bulb. And this is in the sweep circuit. So this, as you can see, it's connected directly to a synchronous control here. So the timing is absolutely crucial. You can see sweep rate right here. So if we look up the function of DS101, I have the actual spectrum analyzer manual right here. In order to make this thing more stable, I designed a circuit that would be regulated for a vacuum tube in here, and it would keep the tube lit all the time, and it was a regulated voltage, and that really helped with stability in the spectrum analyzer. I'm using that spectrum analyzer right now as a pan adapter for my radio. What I'm going to do is I'm going to put that scope back into its case again, and we're going to use that old spectrum analyzer on the old-time workbench. So we'll fix some stuff with that very nice old spectrum analyzer. It's made by the Singer Metrics company. So you can see down here, it explains this. So the electrostatic effect of voltage pulses appearing on this coating will change the voltage required to cause E101, the sawtooth discharge tube, to conduct. A pilot lamp, here we go, DS101 is located adjacent to E101. So E101 again is this, E101 is this little NE16 bulb, right? Adjacent to E101. The function of DS101 is to maintain a constant ionization level in E101 by the photoelectric effect, thereby maintaining a constant conducting voltage. So very, very important. If DS101 is not lit, so basically if the bulb is burnt out, erratic operation of the sweep circuit may occur, right? Because the thing is in, total darkness underneath the chassis and it's shielded. It even has a bottom cover on it, right? So it's very, very important. Now, some of the tubes used in different service way back when, they would actually put a little radioactive material, a little bit of radioactive material inside the vacuum tube. Usually it has a very short half-life, around 5 years, something like that. If I remember correctly, I think cobalt-60 is one of the little chunks of radioactive material that they put inside the tube. Very short life, lifespan for that. So most of the tubes nowadays, of course, that's, I think if I remember correctly, that will decay to nickel. At any rate, so they're getting, the tube, that little piece of radioactive material in there wouldn't be really doing anything anymore. So back in the day, of course, it would be a big deal, it'd have a chunk of radioactive material inside of a tube. But nowadays, again, it's been years and years, right? These tubes were made in the 50s and the 60s, right? So that's long since tired. So if you were to still have that tube, chances are the tube would still be good with that, little chunk of radioactive material in there. It's just that you would now need a light source because the radioactive material is pretty much fizzled out. So that is the purpose of DS101, or a lamp close to a neon bulb, say in an oscillator circuit. And this, again, as you can see, is the sweep section in this spectrum analyzer. So I have your next piece of trivia for you. This was a little bit too easy. A lot of you got this answer in the post, so now I got to give you something a little bit harder to figure out. So that's coming next. Here is today's trivia question, and I'll answer this in the next video. What is the function of this device? What does this thing do? Extra points if you know the actual part number of this device and where they use these things. So I'll give you a quick view of how this thing looks inside. And what it looks like on the outside. So it's pretty obvious what it is, but what does it do? Might be a bit of a hint there too, if you can see the color of the glass. See that? When you look at the paper through it. So that's the trivia question for today. Leave your answers in the comments below. And let's see how many of you get this one right. And if this is too easy, it'll just get progressively harder and harder because I've got some very strange devices. Thanks for stopping by the lab today. I hope you've enjoyed this video on this small Millen scope. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this in the near future. We'll be taking a look at vacuum tube and solid state electronics alike. So there are a lot of neat devices coming, maybe even some stuff you haven't seen before. So there will be a lot of troubleshooting, repairs, restorations, and even circuitry design on this channel involving vacuum tubes and solid-state electronics. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course. I'll put the link just below the video description under the Show More tab. So just below the video is the description, and just below that description is a Show More written in capitals. If you click on that, it will expose the link. Click on the link and it'll take you right there. I'm also on the verge of releasing another invention in design as well, so you're definitely going to want to check out that link. All right, until next time, take care. Bye for now.